it would in inches cubed. So it would be inches cubed per minute.
Okay.
And then on the right here, dv dt is 4 pi 36 squared times 3. It's going to be obviously a lot larger, but I think they're just asking you to sort of compare, what's going on here. So this is 15,552 pi inches cubed per minute. And that's everything for part A. So let's try to answer part B. Do you have any, do you think it's still all multiple choice on your test?
Yeah.
Okay. So, there would be an answer that would match why the rate of change of the volume of the sphere is not constant. So what they mean by that is the radius went up by 4.
Yeah.
But the volume rate of change went up by more than 4. In fact, it went up by 16. The reason is that the radius is squared.
Yeah.
Which is why it actually goes up by 16 instead of 4.
Okay.
All right. So 14 similar, 15's different, I guess. We could do 14. I'm not trying to say not to. It's slightly different, but it's 14 is asking you to solve for the RDT. I'm gonna give you dv/dt. Would you like us to go through 14?
We can. These are all the problems I have today. So once we're done with that, we're done. So we can go through as many as we can get through.
Okay. Yeah, all right. Spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. So that's your dv/dt. You can tell by the units, it's 800 centimeters cubed per minute. The fact that it's centimeters cubed is an indicator that's a volume. You can use the /min if you want. So because it's a spherical balloon, again, the volume is 4/3 pi r cubed. dv/dt is 4 pi r squared dr dt, just like in the last problem.
Right.
Yes, no, maybe.
Yep.
You're talking, but I can't hear you. Maybe something changed.
Oh.
Looks like you're
Can you hear me now?
still talking.
Huh. Hello?
Hey, it looked like the Zoom just crashed, so I apologize.
No,
Can't
that's
do anything
okay.
about that.
I thought it was something on my end that I was doing wrong.
Typical is to say, well, there must be an issue on the customer's end because I do this, 8 to 10 hours a day. But where I was leaving off here is were you okay with how this was
Yeah.
derived?
Yeah.
Okay, so this time we're interested in solving for dr dt.
Right.
So to do that, we're gonna clear out the of 1 4 pi r squared, 1 over 4 pi r squared, like that. Okay, so dr dt equals 1 over 4 pi r squared times dv/dt. Like that. So the radius in part A is given as 30. So we got to do this for radius of 30 and dv dt equals 800. So the rdt becomes 1 over 4 pi 30 squared times 800,
Right.
which is 1 over, I'm going to leave it like this, 4 pi 900 times 800. So we can get some cancellations there. We get zeros canceling, that 8 cancels the 4, leaving 2. So it ends up being 2 over 9 pi centimeters per minute. The reason it's centimeters per minute is because the radius is in centimeters and the time doesn't change. It's still per minute.
So how can we tell the difference if we're solving for dv versus dr, like in the problem?
Yeah, good question, because that is the key thing here. It
Yeah.
says find the rate of change of the radius. That means drdt. In the previous problem, it said find the rate of change of the volume. That's dv dt.
Oh, okay, okay. That makes
It
sense.
tells you. I mean, there's no, you gotta know what words to look for.
Yeah, I just wasn't sure if it's like based, because I know you were saying based on the units, so I didn't know if in the problem it said like differently, but that makes sense.
The units tell you what you're given. You know,
Right.
they tell you, okay, you're given cubic centimeters, so they're telling you which one you're given or not. So A, the radius is 85. dv dt equals still 800. So again, your dr dt is 1 over 4 pi 85 squared times 800. And so I don't know how well this one reduces. I'm gonna go to the calculator and see if I can get some help here. Right, let me go and do this. So this reduces to 8 over 289 pi centimeters per minute. Maybe yours will be exact. Maybe maybe you have to put it in and get a numerical approximation.
Okay.
Same thing here. Explain why the rate of change of the radius of the sphere is not constant, even though dv dt is constant. And again, it's because it's radius squared down here
Right.
in the bottom. Same reasoning. And it's in the denominator. That also makes it worse.
Yeah.
All right, 15A is pretty quick. As all edges of a cube are expanding at a rate of 6 centimeters per second. So that's like straw cube here. X, X, X. So that means it's dx dt 6. The edges refers to the side length. The side length is x. So what's implied here is that you know how to find the volume of a cube, which is x cubed. And then you have to be able to take a derivative of this. So dv dt equals 3x squared dx dt. So in this case, you're solving for, it says how fast is the volume changing? That's dv dt.
Yep.
That's 3 times 6 squared times 6. So that's effectively 6 cubed. That's 216 times 3 is 648. And then units here, it's centimeters cubed per second, because the units of volume are cubed per unit time, which is seconds.
Okay. Yeah, that makes sense.
Okay.
Honestly, I think the word problems are a lot easier than the problems that we were doing in the beginning.
That's good. Good to hear. 25 is kind of the next one I see. Is that where you'd like us to go?
I believe that's the one. Let me check real quick. Yes, the air traffic control.
Okay. I know this problem gives a picture. Picture really, really helps. Usually you have to make the picture. So let's read it here and see if we can come up with how it does it. An air traffic controller spots two planes at the same altitude converging on a point as they fly at right angles towards each other. One plane is 225 miles from the point, moving at 450 miles per hour. The other plane is 300 miles from the point, moving at 600 miles per hour. At what rate is the distance s between the planes decreasing? So let's just say we didn't have the picture and we had to draw sort of a triangle. This is, you generally get a triangle problem, whether it's an airplane or people running or a ladder. It's 225 miles down here. And this is very important. The x dx dt is 450. Now, I'm going to call that negative because it's moving left. That's typical convention to do that.
Okay.
Now the other direction here, kind of the same thing here. It's 300 miles away. And I like to use the arrows to show the rate of change. Here, I think that's a good strategy. It's moving minus 600, and that's dy dt. The reason it's y is because, well, it's in the y direction, right? That makes reasonable sense here. Now, the next thing it says, at what rate is the distance s between the planes decreasing? So here's s. S is the distance between the planes. We can find that from the Pythagorean theorem. This might be another thing to write down if you don't remember it. So s, to find s, it's 225 squared plus 300 squared equals s squared. So s is the square root of 225 squared plus 300 squared. That feels like this could work out nicely. Yeah, it does. You want to grab a calculator and
Yeah. I got 375.
we're good. Okay. So that's the current distance, but like every time this moves, it gets smaller.
Right.
Okay. So now what I think is hard here for most students is you have to write an equation at the time. Like it's not given where it's a sphere or a cone or a cube. The equation is x squared plus y squared equals s squared. And it is a variation on the a squared plus b squared equals c squared. I'm using x because x is typically the horizontal, y is typically the vertical, and s is given as this kind of diagonal. Is that okay?
Yeah.
All right, now when we take a derivative of this, I think this is perhaps the most confusing part. It's kind of like an implicit derivative, but everything has a rate of change because everything is changing with respect to time. So what I mean by that is the derivative is 2x dx dt because x is moving
Okay.
plus y squared 2y dy dt 2s ds dt.
Okay. Yeah, that makes sense.
Right now, you have to go back, like, what are we solving for? We want the rate of, at what rate is the distance s between the planes decreasing? We're solving for ds dt. we want to know how, like this rate here between them. So to do that, you just divide by 2s. So this becomes x dx dt plus y dy dt over s. And this is a good point. Like, let's just say you did this first. That's a good point to say, okay, I need a dx dt, I need a dy dt, and I need an s. And you actually have all those. You have all those numbers from the problem here.
Right.
All right, so that's a good sign. So I'm actually going to copy this down, so I don't have to keep scrolling. But that here. So it's 225 minus 450 plus 300 minus 600 over 375. Okay. So grab a calculator. Why don't you calculate that for us, please?
Negative 750.
Okay. Now, are you surprised that the answer is negative at all?
Yeah.
Okay, so think about the context of this problem. Is the distance between the planes getting bigger or smaller as they get
No.
close? That's why it's negative.
Okay. Yeah, that makes sense.
Okay. It's got to make sense. Like if you have to have some, have you taken a physics class before?
Yeah.
Okay, so like you get to choose like positive and negative, but you have like your answer will be consistent with your conventions.
Right.
So just keep that in mind. Now, how much time does the air traffic controller have to get one of the planes on a different flight path? So the kind of the nice way putting this before the planes collide. Um, basically, you want to know how much time do you have to until this distance goes to 0. So it's converging at 750 miles per hour. And there's only 375 miles to go. So what will happen in 30? So how do you, it's kind of like you're driving to Phoenix and you're going 80 miles per hour and you've got, well, let's use better numbers. Let's say you're driving 60 miles per hour and you have 30 miles left. How long will it take you?
So 30 miles left and you're going 60 miles.
Yes. 1 mile per minute. You've got 30 miles left.
Should just take 20 minutes, right?
30
Oh,
mile per hour.
yeah, 30. Sorry.
So the same thing applies here. So it's like, well, how do we do that? You take its distance equals rate times time. Time is distance divided by rate. Your distance is 375 over 750, which is 1/2, but it's in hours. So that's 30 minutes.
Okay, yeah.
Any questions on that before we move to 31?
Nope.
Okay. All right, the endpoints of movable rod length 1 meter have coordinates x0 and y0. Say figure 1. Let's snip that in here. So they're just saying like the piston, I guess. I don't know. The rod goes down, and then this one goes to the right, maybe. It looks like a triangle again, but then they're giving us this equation. The position of the end on the x-axis is given by this equation. Find the time of one's complete cycle of the rod. Okay. This doesn't seem like this is not a calculus question. This is the time of one period. In the
Huh.
period of a sine wave, sine and cosine have period equal to 2 pi over b. B is the number in front of the variables. In your problem, b is pi over 6. So it's 2 pi over 6, which is 12.
Okay.
So that's the time, 12 seconds for one cycle. Cycle means time for it to go through its complete motion.
Right.
The rest of this, I'm a little unclear on. So I'm gonna go out here to the wonderful internet here and see if I can find someone else's I don't really know what it's asking part B. I mean, I do, but I don't. Like, I don't understand exactly what it's doing. Well, I take that back. I guess we can do this. So this picture here is pretty helpful for part B. The more the rod goes to the right, the lower this goes. Would you agree with that? Like, it has to pull.
Yeah.
So if we can figure out the max of X, then we know how far to the right it will go. And then we can use that because that max X, whatever that is, will go down here. This is 1, and we can find Y through the Pythagorean theorem. Right, so the what is the lowest point reached by the end of the rod on the y-axis? So to do that, we need to go back to this equation here, which I'm going to snip in. Another snip of that. And we need to figure out what is the maximum value of this. So to do that, you have to remember what a sine wave looks like. A sine wave starts at the origin, goes up, comes down, and goes up.
Right.
So we want this max point here, and that is the amplitude. So do you remember what the amplitude is of a sine, cosine?
I don't.
Okay, so here is, it's just this number here. That's the amplitude.
Oh, okay. Yeah. Yeah.
Okay, so that is, we go back to our picture here. That's this from that instead of X, it's 1/2.
Okay.
So to find Y, we use the Pythagorean theorem. 1/2 squared plus Y squared equals 1 squared. 1/2 squared is 1/4 plus Y squared equals 1. Y squared equals 3/4.
Right.
Y equals the square root of 3/4, which is the square root of 3/2.
Yep.
So that's the lowest point reached by the rod on the y-axis. Is that okay?
Yeah.
All right. Finally, we're getting up to rate stuff. So it says find the speed of the y-axis endpoint when the x-axis endpoint is 1/4, 0. So we actually have to go back to the triangle here. And we go back to x squared plus y squared equals 1 squared. All right, so our derivative here is 2x dx dt, 2y dy dt equals 0. And the reason it's 0 is because the length of this rod doesn't change. In the previous problem, the distance between the airplanes was changing, but the rod isn't. So when it says speed of the y-axis, that's dy dt. So 2y dy dt equals minus 2x dx dt. You divide by 2y. And so we have dy dt equals minus x over y dx dt. So but do we have x? Do we have y? Do we have dx dt? And you can't really reuse what you've been using in the other problems. So the answer is no. We don't have much of this. We have x. X is 1/4. We know that. To find y, we have to go back to the Pythagorean theorem here. So we know that x squared plus y squared equals 1 squared. 1/4 squared plus y squared equals 1. 1 over 16 plus y squared equals 1. Y squared equals 15 over 16. By subtracting, y equals the square root of 15 over 16, which is the square root of 15 over 4. So that's y. Now we need dx dt. So the only thing that's going to give you dx dt is the equation for x. Sorry, it's all over the place here. So dx dt, so you have to be able to take a derivative of this. So this is one of those chain rule derivatives. So you might want to, let me actually move this down. Oops, I didn't mean to do that. Let's do it down here because it's going to take a little bit. So it can be written as 1/2 sine u, where u is pi t over 6, like that. So your dx dt derivative of sine is cosine times u prime. This is this, and you just substitute back in. The derivative on the right here, pi over 6 times t is just pi over 6. The derivative of t is 1. So we have 1/2 cosine pi t over 6 times pi over 6, like that. Now we have to evaluate it because we want the derivative at a certain point. We want a derivative when it's 1/4, when x is 1/4. So we need we have to put t equals 1/4 in here. 1/2 cosine pi 1/4 pi divided by 6 times pi over 6. And that I don't think works out all that nicely, which is a little surprising here. Let me just double check this. Yeah. Okay, so I made a mistake here. So this is all fine. Forget about this last part for a moment here. And apologies, this is just a weird problem. What x means 1/4. So 1/4 is x equals 1/2 sine pi t over 6, like this. So if you multiply everything by 2, you get 1/2 equals sine pi t over 6, like this. So then you have to solve for t here. So you solve for t by recognizing that sine equals 1/2 on the unit circle when the angle, I don't want to say this. Let me know if I've lost you because this may be unclear, really unclear. In the unit circle here, sine is the y value. That happens at pi over 6.
Yep.
So pi over 6 is the value of u, and that has to equal pi t over 6, which occurs when t equals 1.
1. Okay. Yeah.
So the reason we had to do all that is because that's the value you're supposed to put in here.
Okay.
is t equals 1. So you had to, I was putting the wrong thing in for the value there. So t equals 1. So we have 1/2 cosine pi over 6 times 1 times pi over 6. Cosine of pi over 6 is square root of 3 over 2 times pi over 6. So we got square root of 3, we got a pi, and we got a 24 there. And now we can put it all together. We can go back here to this. X is minus 1/4, y is 15 over 16, and dx dt is this. We'll get that in here. Here we get that. So the fractions you flipped, so you end up getting 16 over 15 times minus 1 over 4, which ends up being minus 4 over 15. Square root of 3, we got a pi, we got a 24 here. So the 4 cancels with that, you get 1, you get 6. Minus pi square root of 3 over 90, maybe. Any questions on that?
Nope. That makes sense.
Okay. So we've already done 36 a couple of times, so I don't think there's any reason to do that problem. We've already sort of talked about the fact that the yeah, there's the side lengths, they don't change, especially if it's squared. When things are squared. So we can go right to 37, I guess. Okay. There are a couple of classic problems here they're not giving you. One is the ladder leaning up against the wall. The other one is usually it's a person walking away from a light post.
Yeah.
And yeah. So, all right. So here we go. This is true from physics. The equivalent resistance of two circuits in parallel is given by this equation. And they're saying everything's measured in ohms. They're telling you R1 and R2 are increasing at rates of 1 and 1.5 ohms per second. So what that means is R1 equals, I'm sorry, dR1 dt is 1 ohm per second. dR2 dt is 1.5 ohm per second. So at what rate is R changing when the R1 is 50 and R2 is 75? So this is most similar to the triangle problem. Okay. We're going to do it kind of the way I guess most students do is we're going to take a derivative of this first. So you may want to rewrite it as r to the -1 equals r1 to the -1 plus r2 to the -1 just to make it easier for you because it's power rule.
Yep.
So this is minus r to the -2 power equals, I'm sorry, already messed up. Because it's a related rate, you have dr dt. So you have minus r1 to the -2 power dr1 dt plus minus r2 to the -2 power times dr2 dt. And if you can see, I'm kind of it's good to take your time here.
Yep.
So the way to rewrite this here is this is really -1 over r squared dr dt, and this will look a lot better, equals -1 over r1 squared dr1 dt plus -1 over r2 squared dr2 dt, like that. So we were trying to solve for dr dt right here. And the reason we know that it says at what rate is r changing when these things are happening. Okay, so to solve this, we're going to multiply everything by negative r squared on both sides. So what this looks like now is that dr dt equals, just copy and paste here, rewrite all this, equals all of this times negative r squared. So we have to figure out, do we have each of these things? Like, do we have r1? Yes. Do we have dr1 dt? Yes. Do we have r2? Yes. Do we have dr2 dt? Yes. Do we have r though? We do not have r, but we can get it from this equation. So to solve this equation, you multiply everything by r. So you have 1 equals 1 over r1 plus 1 over r2 times r. And then you divide everything by that. So you get r equals 1 over r1 plus 1 over r2. And you probably did this in your physics class. This would have been the second semester physics, mechanics, and then they give you E&M. Usually do some of that's in there. So 1 over 50 plus 1 over 75. If you got a calculator, would you mind jumping in here for the calculation, please?
Yeah. $30.
It's 30. All right. So good news. It's a nice number. So now we go back to this line right here, and now we've got everything. So we got over 50 squared times 1 plus negative 1 over 75 squared times 1.5. All of this times negative 30 squared.
Negative 0.12.
Be positive because these two add together, they're both negative times and
Oh, I didn't see my bad. Yeah, no, it's because I didn't see the first -1. I didn't see the negative on that one.
All right.
But yeah,
Hold on to your answer here. I'm doing the same thing here.
I got 0.6 though now that I changed it to a negative, positive 0.6.
Yeah, I got 0.6.
Yeah.
As well. That would be ohms per second or whatever it is. This is a really tough problem because of the subscripts, because you have to solve it. Like it's a very good problem, but I mean, I don't know. You have to kind of decide if this person that's given the test is gonna
What the? Sorry.
do that. I didn't hear anything. So yeah, I mean that is it. For there. I mean, can we stop a little early today?
Sorry, my fridge is making a really, weird noise, but yeah, we can. I'm good
All
for
right. Very good. So,